Okay, so good afternoon and welcome everybody to the next seminar presentation for the Systems Modeling and Data Analysis Research Group. Today we have Sudyne who's going to talk about his work, and today he's going to enlighten us on practical AI, applying machine learning, natural language processing, and ontology engineering within knowledge representation to promote industrial symbiosis. So I hand over to you, Sudyne, to give us your presentation.
Thank you, Zamishka. Prof, you want to enable share screening? Screen sharing. Okay, thanks, Zamishka, for introducing me. Hi, everyone. Thanks for being here. Like Zamishka said, my name is Sudyne. Most of you know me, and my research is focusing mainly on knowledge engineering and ontology engineering as well within the sphere of knowledge representation, because we're working for practical outcome in our group project of Chemicals Without Borders. So let's just get straight into it. So some of the deliverables for this presentation are listed here, and I will be discussing most of these on a high level. And because of the information density of my topic, and this is the first presentation I've done to the group, if there are any questions or any discrepancies, I will do my best to answer them at the end during the question and answer session. So just getting straight into it, I, as well as many others in the group, started working with algorithm development, but because of my field of research and where it kind of specializes, I'd had to spend a significantly larger amount of time actually understanding algorithm development and the runtime and efficiencies and so on and so forth. Prof knows I spent about 2 months just looking at algorithm developments and reading into varying degrees of depth with the algorithms and how they work together, use cases and so on and so forth. And these are needed as well for the practical applications and as things link together, which I'll mention a bit later. So the natural step after working on algorithm development was the natural language processing aspect of things, and this is something which I think we can't get away from in our Chemicals Without Borders project. We all need to have that pre-processing step and to have the cleaned text, so to speak, in order to work with our system that we have in place. So I spent a fair amount of time experimenting with the available libraries and their capabilities as well, and also spend some time combining the libraries in order to synthesize some deeper meanings and observing the connections that were available to be formed between the entities depending on the libraries used. So there were some dependencies investigated, like I said, and I have a few pros and cons of the libraries as I work through them. So just to kind of outlay how I've worked on things and to take you through my thought process, there are these conventional parsers and parsing systems which are available in Jupyter and Python. Examples are the natural language toolkit and so on. So I first worked with that, and then I looked at a bit more modernized libraries and kits, for example, being Spacey and the tools that are provided therein. And thereafter, the combination of all this really comes in when you look at concept maps and graphical networks and links, which is where I currently am at. So just to start off with parsing in Jupyter, there are various options available. You have the NLTK, so the Natural Language Toolkit regex parser, the Stanford parser, the Berkeley parser, and so on and so forth. And those parsers listed there, I have had some kind of engagement and involvement with them in some degree or the next. From what I noted was that for the particular purpose which my research looks for, they didn't perform as well when initial testing was done on them using strings, which would typically be found in our particular Chemicals Without Borders project. And these issues, as far as dependency classification and entity recognition, when really extrapolated to large-scale language-based behavior, if you're looking at databases and large data sets, were quite significant problems as well. So just to, for the sake of making an example, I use a simple sample sentence, right? So John is reading a book, and Sonnet 18 by William Shakespeare in the living room. So just to show you some of the inefficiencies which I speak of in conventional parsers, here we have a kind of top-down diagram presentation system from the Natural Language Toolkit, right? And so S is a sentence and NP means noun phrases, and there are a lot of individual tags as well. But if I can just direct your attention to the right-hand side of the tagging system here, you notice that living room is divided into live and room. And we know in this case, live in living room is an adjective, yet it's classified innately as a noun phrase. So this is one of the cases where we do see some discrepancies coming in. And like we said, this is for a very general, simple case. So when really extrapolating this to something of a chemical nature, it really does get a bit more intense, and the problems are more significant. So there are questions with efficiency as well, because these systems here use recursion parsing as well. And scalability issues have been well documented from numerous objective sources, not just from myself and my field of research as well. So the issues with part of speech tagging and certain irregularities in dependencies are something which I couldn't really get away from when using traditional parsing methods. And there seemed to be no direct application of semantic structure analysis using the conventional NLTK parsers. So the better alternative when trying to work around this was to use Spacey, as it was a better alternative as far as efficiency, dependency parsing, and visualization is concerned. So because Spacey is a bit more efficient and works a bit well, the example which I use, which I'm sure we can all understand, is sulfur and oxygen is converted to sulfur dioxide. Simple sentence is a simple string, right? So using Spacey and after the text pre-processing, the output kind of was symbolized in this table, which we can see is quite neat and efficient. So in this table, you have the text, which is found from the string that you have above. You have the lemmatized version of the text. The part of speech tagging here, might I add, is accurate to the T. There's no discrepancies there. The tags as well are just used for the program, and the dependencies here are also accurate as well. The shape and alpha factors are used for the program, and we don't really pay too much of attention to that, but it also is able to identify for you whether it's a stop word or not. And being a stop word or not is really quite essential in our chemicals without border study, because if you have X is producing Y or is being produced by Y, then whether something is being produced, it's a product or reagent, those stop words are necessary. So we need to have that kind of detail. So one of the reasons why Spacey works so well and is that much more efficient than traditional parsers is because it does use onto node 5 for its linguistic dependencies and parts of speech tagging. And that onto node kind of, it's a play on ontology, and that's really what we're alluding to as well. So, dependency parsing within the Jupyter using Spacey, it also has the displacey module. This is something which I recently discussed with Ishaq, and it's really a neat visualization tool and something which is quite useful to us as a group as well. More so than just visualizing the links that are found within the tokens of a string. If you actually look at these arrows and how they're formed and the direction of the arrows, they actually show you the relations between the tokens that are used in your string which you fed in. And this is more than just part of speech or entity recognition. So this kind of relationship is essential, because what we really look for in this type of research is we're trying to construct triples, right? Because triples which are constructed in a kind of subject, verb, object-based notation will then be used to map out really the full spectrum or the extremities of detailed knowledge which our user feeds in. And, we can then get some meaningful connections from that. So, you can see in the bottom, once again, with Spacey, represents things quite well, quite accurately. And it also tells you of that particular token in question, what it's linked to and which actual token it's linked to as the head or the tail of the arrow. And that's essential, when going through large scripts, it can make your life quite easy. So, then looking at how really do we take these triples and do we make it something bigger and something representative of something more significant? So we know that it's quite easy to construct the triples, and there will be the fingerprints used to create the concept maps in future. So the two main methods which I looked at in my type of research was tree formation from the nested dictionaries, and also concept graphs and concept maps and knowledge graph creation. So in both of these cases, we're now closing in on more substantial forms of knowledge representation and having a deeper level of meaning. And obviously with tree traversal algorithms being implemented into the networks, like we said, with tree formation from the dictionaries, these are possible to make the system work much more smoother and give us more control of what we can optimize. So just looking at the tree formation at first, once again, these trees were created with the post-process of the tokenized terms via the nested dictionary. We use the same sample sentence, which is sulfur and oxygen converted to sulfur dioxide. And you see the nested dictionary automatically populated the terms under the parent sort of node, which was convert, which was used in the sentence, and the rest of the sets are kind of null. Using tree library within or treelib within the Python framework allowed for a greater degree of functionality in terms of actually working with the tree, working with the child and parent nodes, and allowing us to run operations on these and sort of query the tree in an intuitive manner. So from left to right, you can kind of see the progression and the extent to which these operations can be carried out. Be it in this case here where we just want to transplant or just isolate a specific branch of the tree with all of its children nodes. In this case here, where you want to kind of reverse the process of sulfur dioxide being formed by air and sulfur and so on and so forth. So as far as knowledge graphs and concept maps are concerned, like I said, we want to use triples in order to represent this kind of network or this deeper system of entities. And they're useful for presenting system linking entities in a cluster together so that the queries can be run based on the knowledge represented in this concept map. And so basically what we're looking for is once the semantic models and the databases, as far as the database engineering side is concerned, have been synchronized and set up well enough, then kind of synchronizing and harmonizing that with the knowledge graph in the Jupyter environment is something intuitive, and I've already shown profits quite possible. So within Spacey for the concept maps, we looked at NetworkX and Matplotlib to make these things possible. So once again, not to overwhelm the group with just lines and lines of code, I'll start with just the isolated case of a branch from the concept map. The first case, like we said, is the branch of the map here. And the first thing to be noted is that unlike in the case of Displacey, this is undirected, right? There's no arrowhead, so to speak. But there are some advanced methods which can be used to basically embed those directed characteristics into such a visualization. And there are some observable irregularities as can be seen. Namely, if I just draw your attention here, so we worked with the same sentence, right? But sulfur and dioxide at the end, because sulfur was already recognized as a subject of the sentence, so the token was previously recognized as a subject, the tool recognizes sulfur here or listed as a compound, right? But the part of speech tag for sulfur dioxide recognizes both terms as proper nouns. So, the program is quite robust in a sense where it kind of works around these clashes which may happen and works quite well. So this is the case of what's possible to be produced, which I produced with the same code using an example taken from Wikipedia with some other text added to it. So why I wanted to represent things in this way is to show that, pretty much the same script that's written in my Jupyter notebook, which can be used for the sulfur dioxide case, can be used for not necessarily scientifically structured data and can represent this accurately as well and still form these links, which may be the case because some of the cases of the documentation in the Chemicals Without Borders project may not be so well scientifically documented. So what's noted about working with Spacey is the fact that the dependency tagging and irregularities are present, like I've mentioned before, but they scale up quite well and it does work quite efficiently. It is possible to go ahead and create our own parsers for the project within Spacey. This is something which is done creating pipes within Spacey, and you can then go ahead and dictate your own rigorosity which you want to look at for these parsers which we create. So all of this information which I've given you beforehand kind of culminates when looking at really knowledge representation and ontology engineering, which is where I'm sitting now. So just to make everyone understand, there's three types of data. You have the unstructured data, which may be haphazardly listed or whatever the case may be. After this is processed and normalized sort of in a database and structured into formalized tables, and so to speak, there are more explicit degrees of information which we can get from the data. So it's a bit more valuable in that case. But really where we're sitting or where we like to be working is this third case here with knowledge, where the degree of information that's expressed from the data is now looking at implicit characteristics, or also known as tacit knowledge which is not necessarily explicitly stated. So that's really what we're aiming for and what we're working on. So as far as knowledge representation methods are concerned, there are techniques used to represent the knowledge that we find from the data, and these are description logics and semantic web languages as well. So the logical formalisms which I've been working with are predicate calculus. There's also frame systems and propositional logic. And this is relevant not just particularly to my field of research, but also agent-based modeling, whereby there's work done with the virtual agent and so on and so forth. It's a tried and tested field and it works quite well. As far as semantic schemas and languages and varying degrees of detail of representation are concerned, I'd like to direct your attention to the diagram on the right. Credit here goes to Tish Shangruza, who constructed this diagram. But as you can see, based on the knowledge which you choose to represent your ontology or to go about structuring your ontology, the further the degree of detail and the more rigorous your ontology can be. So from extensible markup language all the way through to the more widely accepted and well-used web ontology language or OWL, this is ideally where our ontology development for our group is currently happening. So we're looking for that sweet spot between using first order logic and semantic languages to create some kind of amalgamation of knowledge modeling which can work practically for end users as well. So I'll be using the word ontology quite frequently and quite often, and a simple way to think about it is that it's just a kind of simplistic form of a knowledge model. So the ontology synthesis languages that we'll be using as a group are the resource description frameworks and the web ontology language, as I mentioned before. The creation of ontology, which I've already started working on, starts with the ontology specification document. Prof and I have been going through that, and it's currently in the iterative process of being drawn up. This document contains certain aspects such as the extremities of which we'd want our ontology to work, and what are the specifications of our ontology, and also having some kind of questions where we can gauge how well our ontology is working later on in the future. Visual representations of the ontology as well, and the visual side of ontologies does have its place. The most widely accepted aspect of this is Protégé, and there's also the coding representations, right? So this is the back-end work and really where most of the spade work happens. This would have to be done in one of the formalized ontology languages, as I've mentioned before. So the international ontology community really pushes the idea of ontology recycling and reuse, and this is kind of mutually beneficial to you as a new ontology creator, but also as someone who's written ontologies in the past, because if you're a new ontology creator and if you're recycling elements of previous ontologies, the process then goes along a bit faster. But if you're the one who's written the ontology, your ontology is kind of moderated and checked, so it's mutually beneficial. But before any of those ontologies are put to work, so to speak, the synthesis of databases and actually managing these databases, structuring them quite well via administrative programs are also necessary. And I'm currently working using PostgreSQL and MySQL as well. So the question that one can be asking is, Sudyne, how does all of this blend together, and how does this practically work? So ultimately, what it would start going from left to right is it would first start off with the database queries. So you'd have a database query and operation kind of set up via an administrative management application. And then, so once a query is made to the database, the semantic and first order logic systems which we've set in place, which would probably be running via an API, which is programming language independent, will then go into the database and make the queries or whatever the case may be that the user is looking for. And these kind of results and outputs would be returned to the user via some kind of graphical user interface, which can be observed via Protégé, for example, and the query results are presented in a neat formalized manner. So I've spoken quite often about the graphical ontology representations via Protégé, and just a simple case I've drawn up for the demonstration of the group here. So graphical and visual representations of the ontological environments are developed over numerous programs and scripts, and they're quite necessary. It does have its place for ease of linkages between various ontologies, to merge different ontologies together and to create deeper understandings within knowledge maps. So why use a program such as Protégé is simply because for purposes such as ontology publication, knowledge sharing, and to work with some kind of query system within the Java runtime environment which it's based on, it really works quite well, and it removes the stress of having to do this in our own foreign environment. Protégé is within itself linked to the Semantic Web and the World Wide Web Consortium, who are the authors of the OWL and RDF languages. So really does make your life quite easy, especially as an end user. So as far as database operations and management is concerned, structured databases do still have their place in modern analytic frameworks. I'm sure a lot of us may have heard of NoSQL or unstructured databases, so to speak, but really based on what we've looked at, structured databases still do work well, especially in our case with industrial symbiosis. So, we eventually do intend to move this to some kind of global situation or serverless database. And API linkages to the databases is definitely a future goal, so that we can have query and editing independent of the programming languages. So currently what I'm working on is understanding database normalization levels, optimal data representation, and just basic CRUD ops, which are your bread and butter operations within the database itself. There are various available data types within the databases to look at, and it's really worth spending a lot of time looking at this, which I have been doing, because when you have thousands and thousands of data sets and documents, as far as efficiency and as far as working well and optimization is concerned, you really want to have your database set up in the best possible manner. So that's what I've been working on. So as far as the roadmap of the research is concerned, currently, I'm at the point where I'm working with database operations, so understanding the optimum method for database structuring and type representation. And once that's done, there is currently a toy database which I have, and once this understanding is solid, then the database gets populated with our chemicals without borders, scenario data. Then we'd want to take the situation to development of text dependencies. So to work on Python to maximize the potential of the dependencies and linguistic value extraction from the database itself. And I've already spoken to Prof and shown him that it's possible to link from Jupyter to the database administration program as well and run operations in that manner. Then as far as ontology management is concerned, you'd want to use methontology principles to iteratively improve upon the original ontology for the Chemicals Without Borders project, which would probably be a pilot ontology or the first one we have drawn up. We then want to go ahead down the line and look at sharing ontologies and databases, because we would have to publish the ontology online and then look at, the database sharing in a secure manner and think about what kind of user allowances would we want to make and so on and so forth. And then finally, we just want to look at automation and testing to automate linkages and operations as far as possible, and testing the quality of the operation system from a database perspective all the way through to the front-end presentation to the user. And this analysis should be done with statistical methods as well. So just throughout the research that I've been doing thus far, I'd just like to thank a few people, both in and out of the group. They played significant roles in my development as I've come to understand and move through my research in this way. If I forget anyone, I'm sorry. And I'd just like to end with a quote from Brian Cornell, the CEO of Target, who stated in 2019 that technology is going to disrupt the future of work perhaps sooner than we thought. So in the off chance that he is watching this YouTube video, I'd like to say, Mr. Cornell, the future is here, and we are the ones who are writing the script for it. Thank you.
Thank you, Sudyne, for your presentation. I will now open up the floor to questions, and if you can please do so using the raise hand feature. So just to get us started, I actually had a question about the first part where you mentioned you had the accuracy and the parts of speech tagging wasn't accurate for that first method that you used, and then you found one that did actually tag everything correctly. So I'm just thinking now, for when you have a company database that has lots of sentences and lots of information, how are you going to now deal with that, especially when most of that information might not even be relevant? There'll be sort of unnecessary sentences. How are you going to deal with that and then sort through all of that information?
Okay, cool. Thanks, Samishka, for the question. I think this is a fair question, and there are a few ways to look at solving that problem. So the first way is that firstly looking at Spacey and how well I work with it, and especially when I showed Ishaq how it can work. It scales up quite well, so you can technically work with large values of information. If you create a certain pipe within Spacey, and if you model it well enough, it can work and work quite well with entity recognition with large corpora of information, so to speak. There are other ways to go about doing this, and to make sure that entity recognition and dependency is a bit more accurate. One of the ways I can think of is off the top of my head is using so in description logics, there's discourse semantics, which is a term that's used for applying predicate calculus and first order logic towards solving problems and entity recognition in not necessarily consistently represented pieces of data. So for example, you can link entities from a report outputted by a company in 2013 to a report from a company in 2019. So it is possible to do that with first order logic. It is quite powerful. But just even apart from that, I know some of your work as well, working with LDA and clustering, there's a way to perhaps amalgamate your approaches, because you and I have had those conversations before, into this kind of system to make that the entity recognition and those linkages be a bit better and be a bit more accurate. So there are a few ways to go about doing that.
Okay,
Thank you.
so Zamishka, I'd like to just give Sudyne a chance to talk about the main problem or the application of this field. So Sudyne, I think at the beginning you didn't quite mention the what relevance it has to Chemicals Without Borders. You mentioned Chemicals Without Borders, but if you can outline the application, and also if you can explain the term ontology in your own terms for the benefit of the group.
Okay, cool, no problem. So the relevance of this to kind of the Chemicals Without Borders project, simplistically, would be that in your industrial symbiosis cluster that you have, where you have various users, companies, and individuals, if someone were to, for example, put out a query that they require a certain chemical or they require a certain material and so on and so forth, this should ultimately, or the system which we're in the process of setting up, seeks to provide the user with not only a suitable match to what they're looking for, but also kind of by having a deeper implicit knowledge of what the user is looking for based on the domain at which it's specified, can possibly query the user's query to a certain degree and say, okay, if you're looking for a certain chemical, why do you need a chemical? Do you need a chemical specifically for, its chemical requirement, or are you just looking for a chemical which maybe works well under these conditions or promotes an exothermic reaction or so on and so forth? And then based on, the interaction of the program with the user, it kind of structures suggestions to the user where if all the user is looking for is a certain chemical just to achieve a certain purpose, but not specifically that chemical, then it would make better suggestions to the user in terms of linking that particular entity in the cluster to another entity in the cluster, which would be a better match for it for the purpose which is required. I know it's quite a mouthful, but it's essentially advising a user about how to optimize the linkages and the matches which would be required for the purpose that the user needs. And just Prof, to touch on the second part of what you asked, in my own words, what really is an ontology? So an ontology, in my opinion, it's a way of, so it's a structured form of representing knowledge using formalized methods and languages, which specifies the domain of the scope of the knowledge, and also allows for knowledge models to be implemented and to be run and changed within the system, be it using existing algorithms or allowing for collaboration from external knowledge models and concept graphs to be implemented and merged with your existing knowledge map. And that's why it works so well, and it's generally written in a web format because of publication and to allow for external collaborators. It's something which is promoted when ontology engineering is brought up.
So I'd like to just follow up there. On that first part, in terms of the application, what we are trying to do is, as you know, in about 3 projects in the group, what we are trying to do is take a body of text, process that body of text, and then identify groupings, right? Now, one of the difficulties is you may be able to identify a chemical from a body of text. Like if you take a paragraph, you can pull out all the chemicals from there, but you don't know whether that's a sort of a chemical that's being consumed or whether it's being produced. Now, part of this, in a way, the starting point of this is that if you can process the text in such a way, or if you can represent that in such a way that you almost translate a paragraph of text into a flow diagrams, and by that I mean the graph. So if you take your paragraph and extract from that a graph of relationships, then you can determine whether a chemical is being consumed or produced. And you see, once you have a graph like that, you are then able to cross-match it with other graphs. So that's the application here. We're actually trying to form, we're trying to extract the meaning, we're trying to extract structure from flat text. So that's one. And then in terms of the broader intention, in terms of ontology and formalism, that's something I've been speaking with each of you about being able to formalize or being able to recognize the mathematical structure underlying the problem that you are solving. Because you see, there are relationships that in fact, we only deal with a limited set. So there's only a limited set of structures that we deal with, and in fact, just last week, I was looking at formalizing some of the data structures that I work with, and even though there are something like apparently 20 different structures, I was able to represent them all as variations on 3 base types. And you see, one of the difficulties that we have in the group with the multiplicity of methods and multiplicity of problems is that it becomes difficult to understand, what other solutions exist with the problem. So it's an important topic for the whole group, being able to formalize the structure behind the work. And in fact, it's something I'll be asking each of us to do more and more, so that if you have a new problem in front of you, that you are able to classify that problem and then be able to look in the library of available solutions to find potential contributions to that area. So ontology and formalism is something that will likely be recurring themes into the future for us. So sorry, I went off there for a bit, Samishka, but back to you.
Does anybody else have any other questions? Phil?
Yes, no, I'm just trying to get an understanding. It was a very good presentation, very informative. So, I mean, my understanding is you're trying to develop these representations of data, I think through these schematic systems and so forth. But I mean, I just wanted to get an understanding, what data will it be? Will it just be text documents? Because I know initially you spoke about sentences, so I thought about, maybe it was going to be documentations like process descriptions and so forth. And then after that, I think you went into databases. So then I just got a bit lost there. Maybe I don't know, you can explain to me how those linked. Will the documents be stored in a database, and then that's the database? And then the second question is, I mean, you spoke about the toy database. What's the structure of that toy database? Is it the documents, or is it just, if you can just unwrap that, just to help my understanding.
Cool. Okay, so for the first, I think just to answer the first part of your question, so ideally what we'd be looking for would be, in the Chemicals Without Borders project, we're not just looking at like conventional chemistry or chemical matching, you're also looking at process engineering aspects of things as well. So ideally, we'd be looking at sources of information, not just from company documentation, but also from their websites and so on and so forth. As a Mishka's project, because she's also part of the Chemicals Without Borders project, so she's worked on web scraping, for example, and even Ishaq. So he's working on identifying which are the suppliers and consumers. So all of these things are important to know, because when you're populating a database, or when you're populating the databases, it's going to be populated with information from the company documentation, from the websites, and basically any information that we can get or that we have access to from the clustering entities in the form of companies in the Chemicals Without Borders symbiotic relationship. And as far as representing it is concerned, there is currently existing, like I've shown Prof before, there's a rough database that I've made, which currently has aspects such as, like reactions and process units and so on and so forth. So what's going to happen is that once we figure out the best way to represent certain aspects in this database, so representing certain details in this database, what I mean by that is Prof drew my attention to something whereby I was just populating this database with strings, for example, when I first started off doing it. And as we all know, strings may not necessarily be the best or most efficient way to go about doing things. So, if we can use systems such as be it either Word to Vec or whatever the case may be, to represent data in the most compact and efficient way possible, either via integers or Boolean or so on and so forth, and represent this within database tabulation, then querying of databases would not only be faster, but it would be easier and more efficient to work with.
Oh, okay.
Sorry,
Okay, so basically you're scraping all forms of data related to those companies that are in the cluster.
So, sorry, if I can just come in there on the database side, the point is to build a library of the different classes of things there. So the object types, well, number one, your unit operations, number two, your chemicals, number three, the types of separations, the types of reactions. So if you have a growing database of these things, then it becomes easier to convert your text into a graph, right? The main problem by the end of the day is converting the text into a graph. And now, if you have a database that that's kind of the repository of the object types, then that eases the classification process and increases the likelihood that you can produce an accurate graph.
Okay. So they're actually working simultaneously. Okay, I think I get it. Okay, thanks, Sudyne. Thank you, Prof.
Okay, if there aren't any other questions, I just had another question as well. Sudyne, you mentioned you're working in Protégé, which means it's outside of Jupyter. And I wanted to know why, because Jupyter as it is and Python is quite powerful in its own. I mean, it has lots of modules and libraries available. So why would you sort of move away from what you were using and then move into a different format?
Okay, so I mean, apart from just like what I've mentioned here, as far as ontology publication and also working with ontologies and creating ontologies in formalized ontology languages, to kind of get these languages to be up and running within the Jupyter notebook framework would be would be a bit more tricky and a bit more difficult. So yeah, I think it's here. So if I could just go here, so this is actually the Protégé environment itself. And if so the example that I have open was one that I kind of did in a way which would make it a bit understandable for the group. So representing the system in a way which is intuitive to everyone is essentially what we aim for. So when you start off with the overall main parent node of a process or of the whole unit, or for example, this can be extrapolated to the chemicals.borders project. And you see, so on the left-hand side, we have the parent and the children nodes, and it's quite a well-specified system, because if you hover over each node, as you can see, has its own URI, which is linked to the semantic web itself. So the URI is kind of like an identity document for each of these nodes. So if anybody were to work with ontologies and want to take a node from here or work with a node from this particular ontology situation, they would do so via the URI. And just to show you a little bit more of what's possible in this kind of environment, I created just a rough example with lecturers and students, kind of a university situation. And if you hover over like the students, for example, it gives you the object property assertions and the data property assertions. So for example, student 1 is myself, and I put my name, surname, student number, so on and so forth. Student 2 is user Mishka, for example, and then student 3 is Joash, for example. And really why I went ahead to do this, just to make a point to you guys, is that this entire reasoner and this entire linkage works, and it works well, and it can output really viable results, even though, as you can see, the specification for the data objects for each of these nodes are not necessarily specified the same way. As can be seen here, for example, of what I'm talking about, the students are all studying different modules, and even in your case, Mishka, as student 2, I left out your student number completely, just to show you that it is possible. So if you look at data properties, everybody else has 3 and you only have 2. So what I'm trying to say is it is possible here to set up a system where you may not necessarily have to specify the same level of detail for all of the children nodes, but the reasoner within the program is set up so well and maintained so well that it is still able to make these axiomatic and semantic links between objects in the data set. So, being able to do something like this, or just being able to work with this, it does have its place. Like, it is very useful and it works quite well as far as database maintenance and ontology maintenance is concerned. So like I said, it is quite useful in that regard.
Thank you. I think Faisal has a question.
Hi, Sudyne. So I'm trying to just create a use case scenario in my head, right? So Filani cleared up the first part in terms of the types of data you will be analyzing. Can you just give me an idea of what triggers or activates this process, right? So what event occurs for this analysis to take place? Does it happen proactively where the various companies in the cluster are analyzed and you'll provide them with advice? Or does it happen when they request a certain chemical, then this analysis takes place and then you'll advise them?
Okay, so I think ideally based on how it will work, it will work as per request, because you'd have the database set up well enough with information from the companies. But for example, why it would work for a request situation is if a particular company within the cluster wants to sell a particular chemical, for example, and another company may be interested in buying that chemical, then in real time, so to speak, we can kind of forge this link between these two companies, and that will promote the circular economy and saving cost and so on and so forth. Doing something like that at a constant rate, like almost refreshing after certain time periods or whatever the case may be, I don't really think it would be efficient, as a whole. So like we said, as Prof said, the use case is not necessarily constrained to just chemicals and just chemical matching or chemical restructuring. It can also work with chemical process units and also just using chemical plant resources as well. So yeah, that's basically the situation.
So, sorry if I can come in there. Actually, as the host, I can't raise hand. Currently, it's not allowed for the host to raise hand on Zoom. On that, imagine the situation where the Chemicals Without Borders system is up and running, and chemicals plant people are uploading data, and new people are coming on board, and people are coming off the system. So imagine it's a live system, and then you have a new industry partner, a potential industry partner coming on board. And as part of their onboarding, they would upload things like their annual general report. They'll provide the URL to their website. They'll provide the process description of their process. Then the moment they upload those things, the system would mine all that text and translate that text into a chemical process. And then once it has that graph, it can then tell you this industry takes in these chemicals and sends out those other chemicals. And then immediately, once that is known, we're able to do things like match companies and complementary matchings, that is, and do things like that. So it's towards further being able to process text as it becomes available from the different industry contributors.
Yeah, and I think Faisal, sorry, just to add on to the valuable stuff which Prof just said now. Even looking at when I was looking at database design, and just as I was learning along the way, you ideally want to set up your database so that it's possibly able to cope with the high RPS or request per second rate or whatever the case may be. So like Prof said, as far as efficiency is concerned and also costing from our side to set up something like that, the ideal case would be, as a request is made, then we can kind of forge these links with the system.
Thanks.
Thank you.
Okay, thank you for that. Does anybody else have any other questions? No. All right. Well, thank you everybody for your questions. And thank you to Sudyne for answering all of them and providing us with a very good insight into the work that you've been continuing with. If anybody has any comments on the actual slides and presentation. Prof.
So in terms of that, yeah, highlighting the problem, and of course, you've been thinking, and this is to each of you. Each of us have been working on our specific problem for a long time, and it's very clear in our heads what that is. But of course, the audience hasn't been spending the months that we have on that problem. So what we want to do early on is provide a problem statement and just help to understand what it is that we are dealing with, especially in an area which is kind of new to the group. Also, ontology. Although we are all implicitly doing it, not many people may know the term. And like I say, I think it's an introduction to an important field for everyone, which is being able to formalize your work and place it and in a way classify it and so on. So always start with the concrete problem statement and then generalize from there outwards. Okay.
Thank you, Prof.
Thank you, Prof. And thank you to everybody else as well. Is that the end? I don't know.
So you have to be able to close strong as well. So whoever's
He does with a thumbs up.
Let's do that.
That's a very good end in my. I'm sorry. Okay, so thank you everybody for being present today. Thank you to Sudyne for presenting and for all the questions and feedback.